My name is Brühl. I did my doctoral thesis on the direct and inverse nonlinear Fourier transform based on the Korteweg-deVries equation. I denote this analysis method as the KdV-NLFT. This method provides a spectral analysis of nonlinear surface waves in shallow water. I did my thesis at Leichtweiss Institute for Hydraulic Engineering and Water Resources in the Department of Hydromechanics and Coastal Engineering at Technische Universität Braunschweig in Germany. I defended my thesis in February 2014, and this presentation is a slightly modified and extended version, and this is recorded in May 2015. My thesis supervisor was Professor Hossein Umarassi. The reviewer was Professor Alfred R. Osborne from University of Torino in Italy. The research that led to the presented results was funded by the German Research Foundation, Deutsche Forschungsgemeinschaft, DFG, in the projects DFG OU 191 and 192. On this slide, I give an overview on the contents of my dissertation thesis, and then I show which of these topics are selected to presented in this talk. First, the thesis gives an introduction on motivation and objectives. Then I give the theoretical background on the procedure of the KdV-NLFT. I introduce some nonlinear water wave equations, especially the KdV equation. I say something on linear and nonlinear wave theories, and very important, knoidal waves as spectral basis components for the KdV-NLFT. I introduce the nonlinear Fourier transform. I say something on conventional wave analysis methods because I need these results to compare my results with conventional approaches. And I give specifications of objectives and methodologies. Then I describe the numerical implementation of the method. And we have both the inverse KdV-NLFT, which provides the nonlinear free surface, and we have the direct KdV-NLFT, which provides the decomposition of the data. I have some short section on validation and summary and implications. After having finished this theoretical background, I come to the practical application, and I have different cases. First one is the comparative spectral analysis of soliton fission over and behind submerged reefs. Give a position of the problem, the theoretical background of soliton fission. Then describe the experimental and numerical setup. And then I apply conventional methods for the spectral analysis of soliton fission. And after having done that, I analyze the same data using the KdV-NLFT, and I describe the results that can be observed. I have a section on the determination of the influence of different parameters on the number of transmitted solitons, now using the KdV-NLFT. And of course, I give a summary. The next problem that is addressed is the harmonic generation in shallow water. After position of the problem, I give the analysis of harmonic generation in measured wave flume data over flat bottoms, and then some discussions on the analysis of the wave propagation over sloping bottoms. I have a section on global and local effects at submerged reefs, and again a summary on this topic. In the next chapter, I have two smaller problems that are analyzed using the KdV-NLFT. One is the analysis and prediction of long-period cosine wave transformation in shallow water using the KdV-NLFT. In my eyes, that's the most impressive example where the advantages of this new method are extremely obvious. And I have some very few things to say on analysis of long-period primary ship waves using the KdV-NLFT. And again, a summary. And the thesis concludes with a summary, conclusions, recommendations, and outlook. I want to note that I have a website. It's given here. There you can find further information on me, my CV, my projects, and my research. It's still under construction, but it's growing more and more. So I think it's worth having a look. You can find the thesis on my website. And, of course, at the Library University of TU Braunschweig under this link. I have published my thesis as a PDF file, so it's no problem. You can go there, download it, and you have the full results of my thesis if you want it. If you think that things are interesting for you and you want to know more about this, if you want to know what your data might look like in the KdV-NLFT spectrum, or if you have any idea for possible cooperations, collaborations, just contact me. You'll find all the important contact data on my website. The contents of my written thesis is way too much to be presented in this presentation, so I selected the highlighted topics to be presented here. So based on the selection, I have the main topics of this presentation, which are reasons for dealing with KdV and NLFT. I show in the theoretical background how to get in 10 steps from KdV to KdV-NLFT. I show how to get from the mathematics to a Matlab code. That's very brief, and most of the details are given in my thesis, so you can look it up there. Then, that's the most interesting and most impressive part. It's the application of the KdV-NLFT, and finally a summary and an outlook. So let's start with the motivation. Water surface waves and the need for a concept of nonlinearity. If we're dealing with water surface waves in shallow water, we have nonlinear waves. We have to think of how is the wave shape, and based on the relative water depth and the wave steepness, we have different conventional wave theories that can be used to provide best fit boundary conditions for periodic wave theories. So if we have a given water depth and the given wave steepness, we can check in this diagram which of the wave theories provides those wave shapes that have a best fit with the real existing waves for these boundary conditions. If we sort them with decreasing relative water depth and increasing wave steepness, then we find that we have increasing nonlinearity and increasing asymmetry, starting from linear airy wave theory. So we have linear waves, then the waves get more and more nonlinear from Stokes' second, Stokes' 5, Knoedel theory up to highly nonlinear solitary waves. Let's have a look at the normalized wave shapes to see what is the meaning of nonlinearity and how can we see that in the wave shape. Let's start with a linear airy wave. That's a cosine wave that is symmetric with respect to the values. So we have the same value of the wave crest as we have on the at the wave trough. If we have a Stokes 2 wave, this wave is nonlinear but not so much. So the wave profile looks nearly the same, but it's shifted upwards to the positive upper axis. If we have a Stokes 5 wave, we see that the wave crest is going higher, less narrow, so the wave is getting steeper, and the wave trough is getting wider and less deep. For the Knoedel theory wave, so that's the wave obtained from Knoedel wave theory in this region, this process is going on. The wave is going to be higher and steeper, and finally we end up with a solitary wave which has no wave trough at all and does consist of one wave crest. When we deal with nonlinearity, we can differ between two different types of nonlinearity. One is the intra-wave nonlinearity. That's the nonlinearity that occurs within one oscillation of the wave, and we have the inter-wave nonlinearity, which describes the nonlinear interactions between two different waves. But now let's start with the intra-wave nonlinearity. We have definition and determination of the frequency of linear nonlinear waves, and if we do it by the conventional definition of the wave frequency, then we find that frequency is defined as 1 over t. T is the wave period, and so we have constant frequency over the complete oscillation, independent of the type of the wave. So even for nonlinear wave, we have a constant frequency. If we introduce and apply the instantaneous Hilbert frequency, as given here, which is obtained by the Hilbert transform of the data, then we get a varying frequency over the oscillation. So within one wave oscillation, the frequency is allowed to change. So let's have a look at some examples for that. Let's start with the airy wave theory. We have the free surface. It's the cosine wave that we already have seen. The frequency in Hilbert transform is constant because this is a linear wave. So the frequency does not change over the period. And if we apply the FFT, the conventional Fourier spectrum, we have one peak because we have one cosine wave. So this wave is represented in the FFT spectrum by just one peak. That's to be expected. If we look at the Stokes second order wave, the profile is given here. The wave profile looks the same, so just by visual observation we are not able to find any difference. If we have a look at the FFT spectrum, then we find that the spectrum is the same because the higher harmonic that would be expected to be here is so small that it's not plotted visibly here. But if we go to the frequency from the Hilbert transform, then we see that already a small variation in the frequency can be observed. So we have a nonlinear wave. We have a steepening of the wave, a very slight steepening, but we have a steepening, so the curvature of the wave shape is changing, and consequently the frequency is changing over the wave profile. If we go to a Stokes 5 wave, we have that increased wave crest, we have the more narrow wave crest, and consequently in the Hilbert transform we have a stronger variation of the frequency, and now in the FFT spectrum we find the expected higher harmonic wave amplitudes that are necessary because we try to reconstruct a nonlinear wave with a non-cosine wave profile by the linear superposition of cosine waves. So we have a wave shape that is not cosine, so we have to add different higher harmonic amplitudes to the basic frequency to obtain that shape. If we go to a Knoidal theory wave, wave is getting steeper, the variation of the Hilbert frequency is getting stronger, and the required higher order amplitudes also are increasing. And finally, at the solitary wave, it's the same. This trend is going on. We have the variation in the Hilbert frequency, and finally we have quite high higher order wave amplitudes. So these are different ways to represent intra-wave nonlinearity. In the Hilbert transform, we have a variation of the frequency within the oscillation. In the FFT, we apply just linear waves, which have a constant frequency, and so we need higher harmonic components to represent the nonlinear behavior and character of the analyzed data. So variation of the frequency over one oscillation, and here we have increasing number and increasing wave amplitudes of the higher order harmonic components. Let's go to the interwave nonlinearity and its effect on the free surface. If we have nonlinear waves and we want to superpose them because they appear at the same position at the same time, we have to consider that we have mutual nonlinear wave-wave interactions between these waves. In this example, we have two oscillatory waves that are two Stokes waves generated from the NLFT, from the KdV-NLFT algorithm that I implemented and that I used in my thesis. So here we have a Stokes wave, and here's another Stokes wave with a higher frequency. If we superpose them linearly, we would obtain this result, but we have to consider that there are nonlinear interactions between those waves, and to obtain the real free surface, the nonlinear free surface, we have to add these nonlinear interactions to the linear superposition. So this is the expected free surface, the nonlinear free surface that is obtained from the nonlinear superposition of two different nonlinear waves. If we have interactions, we have to think of, might they be neglected? Are they important? Do we necessarily have to consider them? And already this very short example shows that we have significant variations of the free surface. in the linear superposition compared to the nonlinear superposition. So the answer is yes, we have to consider them and we cannot just neglect them. A more classical example is the overtaking process of two solitons. Here we have two solitons. It's a large soliton and a smaller soliton. This one is overtaking the smaller one because it's faster. So we have the space, and with increasing time we have these process going on. So this soliton travels here. It's overtaking the other one, and it's coming out of the overtaking process. And what we can see is that the wave height of this soliton is decreasing. At the center of the process we have two waves that look quite symmetric, and then the higher soliton is getting out of that overtaking process without changes in shape, and the same applies for the smaller one. So it's here, so here, and in the end we have it here. So you can see it's getting out. What we observe is a phase shift, and but not a change in shape. And here we can clearly see that the nonlinear interactions here strongly govern the shape of the free surface, because the components itself, they do not change. We have the still basic components before the collision and after the collision. And that's very important. I want to stress that the Knoidal waves here, so the Stokes waves here, and this nonlinear superposition is calculated with exactly the same algorithm that is used for plotting the overtaking of the two solitons. The only thing that I changed from this to this is that I modified the properties and the parameters of the two waves. So for the algorithm that I implemented and that I applied, it is no difference if I have the superposition of two oscillatory waves or of two solitary waves, which here are plotted as periodic, but these are solitons, and the interactions are calculated automatically for this case and for this case. So I want to say something on my motivation for the implementation of the KdV-NLFT. One is I need just one equation for all wave types. I have shown that diagram. I have shown that I have different wave theories in the conventional classification, and when I apply the Knoidal wave equation in the Jacobi theta function representation, then the intra-wave nonlinearity is automatically considered by the boundary conditions, and I have one equation that represents all different wave types. Second, as I have already shown on the previous slides, I get an automatic calculation of the interactions. So when I apply the Riemann theta function, that's a capital theta, here was a small theta, I have automatically considered the interwave nonlinearity, and I automatically get the nonlinear interactions between the waves. But what is the use for that? For the coastal engineering, that's the field where I'm coming from. If we have original data from space or time series, regular, irregular, from experiments or simulations, we have different analysis methods in frequency or time frequency range. And if we apply these methods like FFT, wavelet transform, or Hilbert-Schwank transform, we have different spectral representations of the results. So if we have different methods, different spectra, do we get different results? And yes, of course, we do get different results based on the analysis method that we have selected. And now we have an additional method, that's the nonlinear Fourier transform. That's analysis data in frequency domain. We have a nonlinear spectrum, and of course this gives different results than the linear FFT spectrum. But how do these different results influence our interpretation of hydrodynamic processes associated with the hydraulic performance of a reef structure? That's the example that I started with. But of course is how do the different results from different methods for the same data influence our analysis and our understanding of the processes, and maybe auch on the determination of equations in the end. So finally, one of the objectives is to determine which method provides best results for analysis of nonlinear processes. In the next chapter, I will present some theoretical background, and I will show in 10 steps how to get from KdV to KdV-NLFT. So let's start with the overview on the concept and the procedures of the KdV-NLFT. First, we start with the Korteweg-deVries equation, the KdV equation, that describes the propagation of long waves in shallow water. And since we are in the coastal region with relatively shallow water and relatively long waves, the Korteweg-deVries equation matches perfectly to describe the propagation and behavior of these waves in the coastal zone. Knoidal waves are solutions to the KdV equation for periodic traveling wave boundary conditions, so we can use the knoidal waves to solve the KdV equation, and therefore we can use knoidal waves as spectral basic components for the spectral decomposition of a given free surface elevation. Jacobi theta functions are a useful representation of knoidal waves. So these knoidal waves, which are solutions to the KdV equation, can be represented by Jacobi theta functions. And that's a preparation for the calculation of the nonlinear interactions in step 5. If we want to plot and deal with waves, we have to think of the wave parameters such as the wave amplitude, frequency or wave number, and phase. That's the same for even airy, Stokes, and solitary waves. And in case of knoidal waves, we also have to apply the modulus. If we have performed a direct KdV and NLFT before, and we have decomposed the free surface, then we can use those wave parameters obtained there. And if we use them for the inverse transform, then we can get back the original data. The inverse KdV and NLFT is the next step. We have the Riemann theta functions. Here we have a capital theta for the Riemann functions. The Jacobi functions had a small theta. That's how to differ between them. By application of the Riemann theta functions, the free surface is calculated as the superposition of the n knoidal waves in Jacobi theta functions, otherwise it does not work, and their nonlinear interactions. So the Riemann function approach automatically calculates the mutual nonlinear wave-wave interactions between the n knoidal waves that are superposed nonlinearly. So we have the basic components, the knoidal waves, we have the free surface, and finally the nonlinear interaction term between these waves can be obtained as the difference between the free surface from step 5 and the superposition of the nonlinear waves, which are represented in Jacobi theta functions and application of the desired or the selected wave parameters. And if we subtract that, then we get the nonlinear interactions. The direct KdV and NLFT provides the decomposition of the data. So for a given signal eta from measurements or simulations in space or time domain, the n knoidal waves are determined that return, if superposed nonlinearly by the inverse KdV and NLFT, the original data. That means that the data is decomposed not into those components that, if linearly superposed, return the data. It is decomposed in those knoidal waves that return if the interactions between them are considered the original data. But in the direct transform, the interaction term is not provided. So we get the wave parameters for each of the determined knoidal wave. And if we want to have the interaction term, then we have to apply the inverse transform afterwards. When we have the parameters of the knoidal waves that have been decomposed from the data, then we can judge whether those are oscillatory waves or solitons. The spectral components are determined adaptively within the range of knoidal waves as oscillatory waves and solitons. This means I don't have to define a desired number of airy-like waves or solitons in the data. If there are solitons contained in the data, the direct KdV-NLFT will find them. If there are no solitons, then the result is there are no solitons. That is meant by they are determined adaptively, and the character of each specific component is depending on the water depth. If we have obtained the results from the direct transform, we can represent them in a nonlinear spectrum. And that consists of two parts. One is the radiation spectrum for the oscillatory waves and the soliton spectrum for the solitons. So after this, we have the knowledge of all the basic components that are contained in a given free surface data. What we can do now is we can do the reconstruction of the original data by application of the inverse KdV-NLFT to the data that are obtained here. We can do a nonlinear filtering by selection of specific frequency range before application of the inverse transform. For example, if we cut off at this range, we leave out all these wave components, all the canonical wave with these frequencies or wave numbers, they are neglected for the superposition. And that is called nonlinear filtering, because we do not only remove those components from the original free surface, we also remove all wave interactions that are caused by these components. And finally, we can do a spatial and or temporal evolution of the canonical waves before application of inverse KdV-NLFT, and that provides the free surface as at any position x for any time t. So we have a set of n canonical waves determined from the measurement of or simulation of the free surface at position A. If we have these canonical waves, we can simply change x and t. We can calculate the new phase of the canonical waves at a specific position B at a specific time. And then we can run the inverse transform and we obtain the nonlinear free surface at the position B at position x and time t. And there is no need anymore for performing intensive or cost-intensive numerical simulations, because we can just simply do it by application of the evolution of the canonical waves. Now let's have a closer look at the different steps. This is step 1, the Korteweg-deVries equation. Here's the mathematical representation of the problem. We have partial derivatives with respect to t and x of the free surface eta. We have the wave celerity. We have a parameter for nonlinearity. That's the coefficient of nonlinearity, and we have a coefficient of dispersion. And if we sum up these 4 different terms, they have to provide 0. If this is not given, then the free surface eta is not a solution to the KdV equation. But now I want to show some little examples just to make clear what is the meaning of that. We have a cosine wave generated from Airy wave theory. So that's the wave profile. It's a cosine shaped wave with a wave height of 2 centimeters, amplitude is 1 centimeter, in a water depth of 20 centimeters, and the wave number is 0.5. Here's the free surface. Now I have the partial derivative with respect to time. So it's this term. I have the partial derivative with respect to x times the wave celerity. So it's this term. And here I plot the function that is derived from the free surface. Here's the nonlinear term. It's this one. And here we have the dispersive term. And as can be seen, the result is, well, it's not, but it's nearly 0. So if it's 0, in this case I found it just by trial and error, just to show that sometimes it's quite complicated to find the solution if you want to avoid complex mathematical operations. So it's nearly 0. So this wave was a solution of the KdV equation. If I change the wave parameters, now I have a wave height of 20 centimeters and a water depth of 10 centimeters. The wave number is still the same, and I plot the different components. I find that the superposition of them does not provide 0. So unlike the smaller wave before, this signal is not a solution of the KdV equation. So we cannot say that cosine waves are solutions or they are not solutions. It's strongly depending on the wave parameters. A last example for a solitary wave now. We have a solitary wave with a wave height of 2 centimeters in a water depth of 30 centimeters. And that is generated from the solitary wave theory using the hyperbolic seconds. So here we have the temporal derivative, the spatial derivative, the nonlinear term and the dispersive term, and we find that it's nearly zero. So also this wave is a solution to the KdV equation. Why knoidal waves? I just have mentioned that knoidal waves provide solutions to the KdV equation, and we have shown that the cosine wave generated here and the solitary wave both have been solutions to the KdV equation. But one of the cosine waves that are generated from another wave equation was not a solution. So by application of knoidal waves, we make sure that the waves that we got, they are solutions to the KdV equation. Whereas linear wave theory, where I just can enter any arbitrary wave height, is not or does not necessarily provide solutions to the KdV equation. Also, it was a cosine wave generated from airy wave theory. The term knoidal is derived from the function Cn, which is one of the Jacobi elliptic functions. It's the cosinus amplitudinus. And if I want to plot a knoidal wave, then this is the equation, and the free surface of that single knoidal wave is a function of the wave height, wave number, angular frequency, and phase, just as we know from conventional wave theories. And additionally, we have a modulus m that strongly governs the shape of knoidal waves. And I have said that in the introduction that one of the advantages of this method is that I have one equation that provides waves that fit all conventional wave theories. And now we have one of the most important properties of knoidal waves, and that's the evolution or the change of the wave shape as function of the modulus. If this modulus m, which is part of the knoidal wave equation, because here it's appearing here, if that approaches zero, then the Cn function, the cosinus amplitudinus, is reducing to the cosine function. So a knoidal wave with modulus m is identical to a cosine wave. If we increase the modulus to 1, then the cosinus amplitudinus is approaching the secans hyperbolicus, the hyperbolic secans. And so for m equals 1, knoidal waves become solitons. So we have the range from linear cosine waves up to strongly nonlinear solitary waves just by variation of the modulus m. So one equation gives as function of m all kind of waves from linear cosine waves over Stokes 2 or Stokes 5 shaped waves up to solitons. And that's one of the most important reasons why knoidal waves are used in the KdV and NLFT as spectral basic components. Now we come to step 3, a further look on knoidal waves in terms of Jacobi theta functions. So, and as you might remember from the introduction, we have intra-wave nonlinearity, and this kind of nonlinearity is considered by the Jacobi theta functions. Knoidal waves can be written in this formation. Here we have the free surface of the knoidal wave. Here we have our theta function. The theta function, as can be seen here, is a linear superposition of cosine shaped waves. The governing parameters are b11, which is a function of the modulus. So this value b11 represents the wave amplitude or the wave height. And we also have k, omega, and phi as for any other usually cosine wave. So we sum up a number of cosine waves to obtain the theta function. Then we take the natural logarithm, we take the second derivative, and finally we do a scaling with 1 over L lambda. Lambda is a parameter that considers the water depth. And finally, this expression provides the free surface, which is a Knoedel wave that is associated to this theta function. How does a Knoedel wave look like? I already mentioned that the shape of the wave and the nonlinear character strongly depends on the modulus. In this plot here, we have the shapes of Knoedel waves. So we have the free surface plotted here over one period and for different values of B11. B11, we start with 20. That's a very, very nonlinear wave. So it's nearly a cosine wave. As we can see here, we hardly see anything. We are in the small amplitude limit, and this wave, if we would have a closer look, it would look like a cosine wave. If we decrease the value of B11, in this plot we decrease this down to 4, then we can see that here the wave crest is rising and it's steepening. We have the occurrence of wave troughs to the right and to the left of the crest. And finally, for B equals 4, we have that shape that can be seen here. So in this wave shape is a typical nonlinear wave shape with a higher and more narrow wave crest and a wider and less deep wave trough. If we go further, we have to switch from this plot to this plot due to scaling reasons. You see here we have up to this value, and here we have this value. And that wave that is plotted here at the corner is the same one as the one that is plotted here. So you see, if we further decrease B11, the solitons appear and the wave height is increasing very strongly. So this equation provides this wave shapes, and therefore we can replace the conventional classification of progressive surface waves, which is given here, by the application of the Knoedel wave equation. But I will explain it in more detail. Conventionally, we have Airy wave theory for linear waves, Stork's wave theory of different order that provides more nonlinear wave. We have the Knoedel wave theory, and finally the very strong nonlinear solitary waves. So if we decrease the relative water depth, we have increased wave steepness, and we have increasing nonlinear properties of surface waves. As can be seen here and here for the Knoedel wave, I denote this as the Knoedel wave equation, just to make it clear that something different from the conventional application of the Knoedel wave theory, which is connected to this area of applicability. So the Knoedel wave equation, as plotted here, gives the surface shape of Knoedel waves as function of the modulus m, and it considers all, or it provides all wave shapes that can be obtained from these waves. And if we use the modulus, we can classify these waves. So for a modulus of larger than 0.5, we have Knoedel waves that look like waves from Airy wave theory, and therefore they are denoted as Airy-like waves. The same is for Stokes-like waves in this modulus range. Knoedel-like waves, these are those waves that are located here, and they are usually obtained from the application of the conventional Knoedel wave theory. And finally, for a modulus larger than 0.99, we have solitary-like waves. So one equation to cover all this range. But we have to be careful because we have a limit here, and the applicability and the the KdV equation is valid only for long waves. So for waves with a ratio of water depth over wavelength smaller 0.22. If this ratio is becoming larger, then the Korteweg-deVries equation is not governing the nonlinear interactions anymore, because then we have to switch to the nonlinear Schrödinger equation. So that's the threshold for the applicability of the KdV equation. Riemann theta functions, as I already said in the introduction, consider interwave nonlinearity. And here I will explain how it works. First, the Jacobi theta functions in the previous slide provided the free surface of one single knoidal wave. The Riemann theta functions provides the free surface of the superposition of different Jacobi theta functions. So here we also have a theta function, and it basically it's looking very, very similar. Here we have a sum, but now we have vectors here for k, omega, and phi instead of single values, and we have a matrix B. In the previous slide there was B11 for a single knoidal wave, and here we have matrix B. As can be seen, this matrix B contains the individual B11 or B22 values of the n knoidal waves that are to be superposed. So here on the diagonal terms, the amplitude representation of the knoidal waves. The off-diagonal terms, they provide the interactions. So here it's the interaction between wave 1 and wave 2, and it's the same here. Please note that for further notation, we consider that B12 is equal to B21. So that is symmetrical from this and this and this and this. So what is the implication of that? We sum up knoidal waves, n knoidal waves, and their interactions. So if we have a 3 by 3 matrix, then we would sum up 3 knoidal waves, but we have 9 components because this 3 knoidal waves cause 6 interaction terms. So you can see we have n waves and we have n square elements in the matrix B, and that's the reason why this method is mathematically and numerically complex. I have an example. If we superpose 2 knoidal waves, so n equals 2, then the theta function, well, note that the theta function here and on the previous slide, it's not the knoidal wave. We have the theta function, and to obtain the free surface, or on the previous slide to obtain the knoidal wave, we have to take the log and the derivative and the scaling. So theta is not the knoidal wave, and this theta, this capital theta, is not the free surface. The interactions between 2 waves are considered as Jacobi theta functions within the theta functions, and the reason is that each value of B is representing one Jacobi theta function. So also the interactions are considered as theta functions, and that's all within the Riemann theta function. And well, for that, back to that example, we have a theta for n equals 2, so we have 1, that's this plus 2 times, and now we have the first element, it's B11, so the first term here, so K1 and Phi1, represents the first knoidal wave. So that's identical to the Jacobi theta function of the first wave. Then we have the second component, B22, K2 and Phi2, that's the Jacobi theta function of the second knoidal wave. And then we get the interaction terms. So due to the matrix notation and the mathematical background behind it, we obtain that term. So we have B11 minus 2B12. That's because of B12 equals B21 plus B22. So here we have the amplitude of the first interaction term between the waves 1 and wave 2. So we have K1 minus K2 and we have Phi2 minus Phi2. So since we have K1 minus K2, this provides a subharmonic component. The last term that has to be considered is has the amplitude representation B11 plus 2, B12 plus B22, cosine K1 plus K2 and Phi1 plus Phi2. So here we have a superharmonic component. As can be seen in the algorithm, if we have n equals 2 and we know the wave heights or the modulus or the values B11 and B22 of our 2 knoidal waves, the interactions are mixed terms and they are calculated automatically. So Further details on this example, I have two Knoedel Stokes-like Knoedel waves. It's the one that we already have seen. On the right column, on the left column, I have the free surface plotted, and in the right column, I have the conventional FFT spectra. Here's the first wave and its spectrum. Here's the second wave and its spectrum. I have selected log scale, otherwise I would not have seen all these peaks. If we have the linear superposition of these two waves, we get this surface. If we have the linear superposition of the two spectra, we get this spectra. And this spectra of the superposition of this is the same as the application of the FFT to this signal. So, but that's expected. I just want to show that this spectrum of the linear superposition shows the peaks that are already contained in the individual spectra of the two Knoedel waves. As I mentioned, if we do the superposition of nonlinear waves, we have to consider the mutual wave-wave interactions. So this is the interaction term, and as you can see here, we have a lot of additional peaks. Remember that all the peaks that are found here are already contained in the two Knoedel waves. So all the peaks that are added here, they are new. And these new peaks arise from the interactions as have been shown on the previous slide. So we have subharmonic and superharmonic components automatically calculated. If we have a closer look at that, for example, the component with a frequency or wave number in this case of 0.2, so we are here. This arises from the interaction of, here it says k, wave number 1,3 minus 2,1. So 1,3 it's this one, it's 1.2, 2,1 is this one, so 1.2 minus 1 provides 0.0, so that's the subharmonic component of the interaction between this component and this component. And there we have K21 minus K12. K21 is this one, and minus K12. 2.1, what's this one? So 1.0 minus 0.8 also provides 0.2. So that's another subharmonic component hidden within this that arises from the interaction of this one and this one. So if you go through stepwise through all the wave numbers, you can explain where these peaks are coming from. They are either subharmonic components or superharmonic components, or sometimes both. Finally, we obtain the free surface from the nonlinear superposition, and that's obtained as the superposition of this wave and the interaction term. And if we have the conventional Fourier spectrum, we can see that all the peaks that are contained here and here now can be found in the spectrum. So finally, the nonlinear free surface contains FFT spectra entries that are not contained in the two waves that are superposed. So there is a generation of additional super and subharmonic components in the algorithm, and I already mentioned that they are calculated automatically by application of the Riemann theta functions. In the algorithm, the inverse NLFT provides the free surface. So I get this result. I know the two incident waves, this one, and when I subtract these two waves from the free surface, it's done here, free surface minus the two waves, then I obtain the interactions, because the interactions arise from the difference between the linear superposition of those and the nonlinear free surface that contains the interaction. So up to now we have been introducing the basic basic equations and Knoedel wave functions. We had the inverse KdV-NLFT. Now we step to the direct KdV-NLFT, where a given signal is decomposed. The principle is that we have a given free surface data, either from experiments or simulations. We do a nonlinear decomposition into Knoedel waves and interactions, but in this algorithm the interactions are not provided. So when I want to have explicitly have the interactions, I have to run the inverse transform afterwards. So now we have n knoidal waves, and we have amplitudes, phase number, frequency, and wave number, and we have the phases and the modulus of each of this wave. Then we can classify the waves by either as oscillatory waves or as solitons. If the modulus is smaller than 0.199, then we have oscillatory waves, and the classification is, as I already have said. We get wave numbers, frequencies, and amplitudes, frequencies, wave numbers, and phases for each of the waves. If the modulus of a component is larger than or equals 0.99, then we have a soliton. And for the solitons, we obtain the amplitudes and the phases. Since for all solitons, by definition, the wave number is 1, because we only have one wave in the analysis window. And for all components, we get the modulus m, which is a representation of the nonlinear character. We get the matrix B, since m and b, m is a function of b or vice versa. And we get the off-diagonal elements from this equation, because they are automatically calculated as functions of the wave numbers. So if we have two waves, like here it's waves 1 and 2, we can calculate from the wave number of wave 1 and wave 2. And as I said, they're symmetric, so these values are the same. Now we have all required data, and we can represent it in a nonlinear spectrum. And that presentation style is similar to the well-known conventional FFT spectrum. First, we have an oscillatory wave in the radiation spectrum on the right side, and we have a soliton spectrum on the left side, where the soliton results are presented. In this example, I have taken this data. There is a leading soliton followed by trailing oscillatory waves. And first we plot the oscillatory wave amplitudes as functions of wave number and amplitude. So that's completely the same as in the conventional FFT spectrum. Second, we plot the soliton amplitude. So in this signal, the NLFT detected one soliton, and it is plotted here with its amplitude. Well, if there is no soliton in the data, especially because of the large relative water depth, then no soliton is found. So this method is adaptive in this respect. And finally, we plot the modulus for all components. In the algorithm, the wave numbers of the solitons are provided as complex numbers, which has no physical meaning. But to avoid mixing of the two spectra, usually we plot the solitary wave amplitudes on the left side in the negative part of the spectrum. Otherwise, they would be plotted here, and then depending on the scaling on the axis, I have a mix between the soliton results and the oscillatory wave results. Now that we have the modulus, we can classify the waves if we want to do that. Here it's one soliton. We don't have a knoidal-like wave in this example. We have 1, 2, 3 Stokes-like waves with decreasing nonlinearity, and all the other waves, they are airy-like, and the smaller the modulus, the more they really have the shape of cosine waves. So that's the information that is plotted in the nonlinear spectrum. The question is what to do with the results. Some things have been already said, but first we can do the usual analysis as with all other spectra. So we have a spectrum, we have results, and we can do an interpretation of the results with respect to the underlying physical processes. We can compare it with the results of other spectra, for example, fast Fourier transform, Hilbert-Rank transform, wavelet transform, or any other kind of analysis. And we can compare the results with other nonlinear spectra from other wave or structure parameters. So that's something that is done with FFT spectrum as a normal procedure. If we want to apply the inverse KdV-NLFT to return the original data, we just take the data from direct KdV-NLFT, we put these data into the inverse transform, and the nonlinear superposition of the determined Knoidal waves and the calculation of their interactions provide the free surface, or to say, it returns the initial free surface that was analyzed in the direct transform. Second, I already mentioned nonlinear filtering. In this example, I have the free surface. I did the direct KdV-NLFT, and I provide and I obtain the result that we have two Knoidal waves that cause this free surface. If we just do the reconstruction as presented here, then we just put these two waves in the inverse transform and we get back the original data. If we want to do a filtering, in this case, for example, let's remove this wave. So we just end up with one wave. Since we removed this wave, we also removed all the interactions that are connected with this wave. So in the inverse transform, in this case it's quite simple, but we just have one wave left. So the result is that the free surface is this wave, so it's not the same. But as I mentioned, we did not remove the deleted components. We also removed the interactions that are connected with that. That's why it's called nonlinear filtering. And finally, if we have these waves, like in this example, these two waves, let's say we have measured them at position A. We run the direct KdV-NLFT, that was the free surface. In this example, we have three Knoidal waves detected. This is the linear superposition of these waves, and we have the interaction term. That's a local value that is depending on the phases of the waves. So we discard these local interactions. Then we do a spatial and or temporal evolution of each of these waves to get from point A to point B. So now we have different phases of our waves. Now we apply the inverse transform. We can calculate the new local interactions at this position. It's given here. And if we sum up everything, we get the nonlinear free surface at position B. And maybe you have noted we have not done any complex numerical Ransworth simulation. We just did an analysis. We changed x1 for each of the waves and or t1. So it's a simple wave propagation, wave evolution. And then we calculated the interactions. And we have the expected free surface as a completely different position. Well, just by application of analytical wave properties. So that's another very, very big advantage of this method. Now, just very short things on how we get from the mathematics to the Matlab code. We have to solve the Schrödinger eigenvalue problem, which is a mathematical approach. The idea is that we apply the inverse scattering transform on water surface waves, and to say it more general, we have an analysis of unknown wave structures by, I would say, like a treatment with known mathematical functions. Let me explain that. We have an unknown structure, it's our free surface. We know the surface propagation, the surface elevation, but we do not know the inner nonlinear structure. We have no idea, and we cannot say anything about how many Knoidal waves are hidden within, how do they look like, and what are the interactions. So we cannot say that, we don't know that. We have a known function, it's the Schrödinger eigenvalue problem, and we throw our unknown structure into that function. So here we have our free surface elevation, and the solution of the Schrödinger eigenvalue problem is done by the software. That's a mathematical and numerical process. And this solution, or this treatment of unknown structure, known function, separates the Knoidal waves and the nonlinear interactions. And the nonlinear actions are discarded. It's like they disappear in the algorithm, but we have a detected system response. So the system response, in this case it's the low K discriminant, does not directly provide the Knoidal waves, but it provides all required information that we need to determine the wave parameters. And finally, after we obtained all the wave parameters from the Floquet discriminant, then we can plot the nonlinear spectrum. To obtain the required results, we have the scattering problem. That's connected with the solution of the Schrödinger eigenvalue problem. We have some scattering matrices. We have Taylor series expansions. And finally, the scattering matrix is calculated. And this scattering matrix provides the Floquet discriminant. So it's delta E. And it's the trace of that matrix. And this Floquet discriminant, that is the plotted blue line that you can see here. So if we have a closer look at that, when we go back to the data with the one soliton, the leading soliton, the trailing oscillatory waves, then we have the blue line. It's the Floquet discriminant that belongs to the analysis of this data. We have a reference level that's connected with the water level that's separating the oscillatory waves in the radiation spectrum and the solitons. Now we have a detailed look on that. So here's the reference level. That's the section here. So here we have the solitons and here we have the oscillatory waves. But I will explain that. First, the most important values are the plus minus 1 crossings of the Floquet discriminant. Here's 0, here's plus 1, minus 1, and these are the values of the Floquet discriminant. Please note that in that representation, the values here between 0 and 1, or from minus 1 to 1, are plotted in linear scale, and for values larger than 1 or smaller than minus 1, they are plotted in log scale. So here are the eigenvalues of the Schrödinger eigenvalue, of the Schrödinger eigenvalue problem. And now we have determined the crossings. So here, these are the black dots. For example, in this, it's the crossing number 12 and 13. They are neighboring. And I determined the crossings, and I determined the eigenvalues that belong to each of these crossings. If I have the eigenvalue, and each crossing here, so this is called an open band, because the Floquet discriminant is crossing plus minus and it's recrossing again. This is the open band. And in the middle of this, I get the eigenvalue, and then I can calculate the wave number and the modulus. And the modulus of this component is calculated from the neighboring eigenvalues that are related to that. And the amplitudes of the solitons, the amplitudes of the oscillatory waves are calculated from the distance between these two crossings for one component, for the next component from the difference between these two crossings. If the curve is only touching plus 1, then we have an amplitude of 0, and this component is not relevant for the reconstruction of the data. And for the solitons, we have the reference level here, and we have the crossing here and the distance between the crossing. So that's really a nearly vertical line, so we don't have any nearly no difference between the two values here, but the difference between this crossing and the reference value, that gives the amplitude of the soliton. And finally, we plot it in the spectrum. That's all that I wanted to say for the mathematics. For further details, please have a look at my my thesis. And the details are given in the book from L. Osborne. It's called Nonlinear Ocean Waves and the Inverse Scattering Transform, and it was published in 2010. And this book really was a big help for me to do all the implementation up to that. And without the book, I don't know if I would have reached the chapter 4 where I was able to do real applications. So thank you, Al, for publishing this book. Now we go to the applications. And I present the example of the propagation of a long cosine wave in shallow water. The propagation of long cosine waves in shallow water is the typical Sabutsky and Kruskal problem from 1965, where they showed numerically that a long cosine wave is disintegrating into solitons and trailing oscillatory waves. In this example, I present the analysis of experimental data. So we start with wave flume data that are not simulated data. I really have measured these waves shown on this slide in the wave flume at LWI in Braunschweig. So I have a cosine-shaped wave with a wave height of 5 centimeters, a period of 16.67 seconds, and in a water depth of 21 centimeters. So it's correct, it's just 21 centimeters. You might say nobody is generating such a wave. Well, I did because I wanted to see what happens. So what I did is I told the wave maker to generate this wave. I had a wave gauge 1.05 meters behind the pedal, and that's what this wave gauge recorded. So after the ramping up, we have a wave that looks quite good, like a cosine-shaped wave. So when I want to know if this wave is a solution of the KdV equation, I did a calculation. I plotted this cosine profile, and I calculated the different terms, the 4 terms of the KdV equation, and that's the summation. So it's not zero. So this long wave is, for the given water depth, not a solution of the KdV equation, and therefore I expect that this wave will not propagate as one stable wave, but it has to show some effects, and it has to change its shape. So what happens? At the wave gauge 41 meters behind the pedal, I recorded this signal. Well, this is ramping up, that is connected to that ramping up wave here. But after the ramping up phase, I have a periodic signal of solitons. So this initial cosine-shaped wave profile disintegrates into a train of solitons. The second one shows the same. So the second wave also disintegrates in the same train of solitons. After 2 waves, I was not able to do further measurements because the reflected waves from the end of the flume came back. And when I go farther down the flume, then the faster solitons here, they start to overtake the lower trail of the previous wave. So at this position, I got this wonderful periodic train of solitons. So what happens? The conclusion is this wave is not a stable wave in shallow water. So this cosine-shaped wave disintegrates. And if I apply the KdV equation, then I already have known that it's not a stable wave. Because if it would be a stable wave, then it has to be a solution of the KdV equation. So it's not. So it's not a stable wave. But what happens if I apply my direct KdV-NLFT to this kind of data? Let us start with the far-field data. I have this signal measured here, and the nonlinear spectrum is this. So here's the reference level somewhere here. We have on the left side, we have the soliton spectrum, and we see that in the soliton spectrum, the software has plotted 11 soliton amplitudes. So we have 11 times a modulus larger than 0.99, and therefore we have 11 solitons. If we try to find them in the data, where they are ranked by wave height or amplitude, then we can determine up to 7 solitons directly, and we say, okay, this one has nearly separated, this one not yet, but experience says there is no doubt that for further progressing, this solitons will disappear and separate. No, not disappear. They will separate from that bore. What about the solitons 8 to 11? Well, we have that trail, and well, it's no problem to assume that with increasing way, even more solitons will come out here, and maybe there are some trailing oscillatory waves as given here, also, although they have very small amplitudes. So that's reasonable. We have a signal where visual observation shows solitons. We have an analysis method that says, well, there are a lot of solitons in the data. And this happened when I applied my KdV-NLFT to the initial signal, measured 1.05 meters behind the pedal. So what I did in both cases, I selected just one period. So here I selected this period, here I selected this period, and I did the analysis just for one period because we have a periodic signal. The periods here show the same waves and the same here. So the result was, well, for me it's what I expected. I guess that for most of you it's a surprise that the KdV-NLFT provides nearly the same results. So in this cosine wave data, my analysis method finds 11 solitons and some trailing oscillatory wave. So what's the reason for that? The explanation is that this wave, as I have shown, is not a stable wave in shallow water. It's not a solution of the KdV equation. So if it's not a stable wave, so what else is it? And the explanation is this wave is a superposition of waves that are solutions of the KdV equation and that are stable waves in the given water depth. So we have very shallow water. So we need knoidal waves, we need nonlinear waves that are stable under these conditions, and these waves usually are solitons because of the very small relative water depth. So solitons are stable waves, and if we have a number of solitons, knoidal waves that have solitary wave shape, and we superpose them nonlinearly, then we have very strong wave-wave interactions between these waves, and these nonlinear interactions have significant influence on the free surface, and that's why the free surface generated from the superposition of solitons provide cosine-shaped wave. So that's not a real cosine wave, but it's a transient cosine wave that is obtained directly behind the pedal. If we go along the flume, we have the cosine wave becoming more asymmetric. We have a bore-shaped wave, and finally, at the front of the bore, the solitons are coming out. So, well, up to now, it's just a hypothesis of me that this is a transient wave generated from solitons. And as we have seen in the example of the two overtaking solitons come out of this overtaking and collision processes without having experienced a change of shape. So in the next step, first I wanted to know if I can repeat these results in a numerical simulation. So I used a Ransworth model, that was the Cobra's UC model from Cornell University and modified by University of Cantabria and Santander. So I used that, I generated a cosine wave, and I have seen the same that I observed in the flume. The wave is getting more asymmetric, I have a bore-shaped wave. Finally, I have the generation of a train of solitons with increasing distance from the wavemaker. The different slopes here are due to different distances between the individual plots. So now I wanted to know, can I do it vice versa? So can I generate trains of solitons that then provide a cosine-shaped wave? And that's what I did. I took this initial wave, I have the train of solitons as shown here. I selected from here one period, so I changed the direction. So now the waves are not traveling from the wave pedal to the end of the flume, or the numerical flume, but they are traveling in the other direction. So I repeated that signal, and I used this multiplied signal section as input for a new numerical simulation. And in fact, I got a periodic cosine wave at one specific position. Here's the plot of this. The train of solitons, since it's a time series, the waves are running from right to left, so the higher and faster solitons overtake the slower ones. And at one position at the flume, my wave gauge showed a cosine wave. So first we have overtaking, we have generation of this asymmetric ball-shaped waves, then the waves get symmetric, they have cosine shape. After that they get back to the asymmetric shape, but in the other direction. And finally, the solitons reappear from that overtaking process without changes of shape. So my conclusion is that, in fact, the numerical simulation shows that a train of solitons is able to provide a transient cosine wave just by the overtaking of different solitons. So here it's again, we have the initial solitons, they overtake each other. Here they are traveling from left to right, since it's a plot over space X. We have nonlinear interactions, they start to form a ball-shaped wave. At this position, the wave gauge shows a quite good cosine-shaped wave. Then the wave turns back into a ball-shaped waves. Here we see the first soliton that is starting to separate. Finally, the solitons are coming out of that. So in fact, solitons and their interactions are able to generate a cosine-shaped wave. So, and what is happening in the flume? In this simulation, I have started with a train of solitons. Then we have that cosine-shaped wave. But if we just say we put the flume here at this position, and we start not with the generation of this waves, but we directly start with the generation of that transient cosine wave, then this wave is generated, but it's not a cosine wave, because physics know very well that under these conditions it's not a stable wave, and the solitons come out. So the part here, it's the same as the part here, starting from here, and it's the same what happens in the wave flume. So I want to have some comparison to other wave analysis methods. So I took the signal measured here. So now it's the signal of the numerical simulation. It's not the one, it's not experimental data, because I have not done these experiments, because I have not the flume to do that. The blue one is the one from the transient cosine shaped wave from the numerical simulations, and the red plot is a calculated mathematical cosine wave, and the agreement is quite well. Now I have run an FFT of the blue numerical line, and we see that we have one significant peak here that represents the cosine-shaped basic wave, and we have a small higher order amplitude that is caused because of these variations from the perfect cosine shape. I have applied the wavelet transform, so here we have that significant frequency, we have the higher order component here, and here we have the Hilbert-Wang transform that gives the main frequency here. And up to now, there is no reason that this wave is anything else but a normal cosine wave. Not a very perfect wave, since we have higher order harmonics, but at least it's a not very good cosine wave. And these conventional analysis methods do not give any hint that it might be something different, but NLFT does. So we can identify the transient character in the KdV-NLFT. First, the signal is not a solution of the KdV equation. So if it's not a solution, it has to be constructed of waves that are solution. The signal cannot be a basic component of the KdV-NLFT. Yes, it's not a solution of KdV. So if we apply the KdV-NLFT to that data, this signal cannot be the result, because it's not a solution. So we need different waves that represent that data. And the signal has to be a nonlinear superposition of at least 2 Knoidal waves. In this case, we had 11 solitons and some oscillatory waves. In the given water depth, h equals 21 centimeters, solitons are solutions of the KdV equation for long waves. If the wave is getting shorter and the wave number is increasing, then also oscillatory waves have been possible. And in the spectrum, you see that you have a quite large range where we have solitons, and only for higher, in this case, frequencies or wave numbers, the oscillatory waves appear. And that's the reason why up to a certain wavelength in this small water depth, oscillatory waves are not solutions, but solitons are. So the cosine shape is caused by the superposition of solitons and their nonlinear interactions, and the transient cosine shape is a function of the phases. So KdV-NLFT is able to reveal that this long cosine wave is not a stable wave, but it's an unstable wave, and furthermore, it can find out which knoidal waves are hidden within that transient wave. So we come to the end, and what I try to explain in detail by the example of that long wave propagation is a very, very important thing, because we can explain different physical processes by transient waves. And if we can explain many things to be caused by transient wave, then we can see why the application of the KdV-NLFT is so important and provides some real good advantages compared to the conventional methods. Each wave shape in shallow water, and that's the conclusion, the most important conclusion of my thesis, each wave shape in shallow water that is not a solution of the KdV equation, so which is not a knoidal wave, is a transient wave that is composed by two or more knoidal waves and their nonlinear interactions. So each wave that is not a knoidal wave can be decomposed into knoidal waves and their interactions. When I apply this assumption to different shallow water problems, then I find that the propagation of long cosine waves in shallow water can be explained by this. That's what I have showed. So I can identify the hidden solitons. I can explain the long wave transformation into Bores and solitons. So if the profile changes from cosine shape to a Bore-shaped wave, then it can be simply explained just by wave dispersion. We have different components with different wave celerity, and so when they propagate with different celerities, the phases change as they propagate, and therefore the interactions change. And finally, the change of the interactions is a effect of the wave dispersion, and so the wave transformation from cosine wave over Bore-shaped waves up to a train of solitons can be explained by, let's say, nonlinear wave dispersion. And if we have the initial data, we can predict the disintegration into solitons. So my analysis method requires a cosine wave, a water depth, and it can say which waves are hidden, and then I can predict in how many different waves components and which kind of wave components this wave will disintegrate in the future. And we can calculate that. If we have a look at harmonic generation in shallow water flumes, then it's the same, but just for a higher water depth. In this case, we have very small water depth, and therefore we have solitons. If we increase the water depth, then that long cosine wave still is not a stable wave, but it will not disintegrate into solitons, but it will disintegrate into other nonlinear knoidal waves, like Stokes waves, maybe also some airy-shaped waves, but it will disintegrate. And so I can explain harmonic generation in shallow water wave flumes as as dispersion effect in shallow water. It's the same here, just does not disintegrate in solitons, but in other kinds of oscillatory nonlinear waves. Harmonic generation, and that is shown in my thesis, and it was first shown in Al Osborne's book, that harmonic generation occurs only in the conventional FFT. It does not occur in the KdV-NLFT, because here the basic components, the knoidal basic components, are constant. They do not change. and therefore only the interactions change, but they are not presented in the nonlinear spectrum. So the interactions are functions of the phases, and since only the interactions change, the nonlinear spectra of this wave and this wave, they would be the same exactly as shown here. This spectrum and this spectrum, they were the same because the basic components, the underlying knoidal waves, have been the same. And that's why harmonic generation does not occur in KdV and NLFT, at least for flat bottoms. If you go to sloping bottoms, you will have harmonic generation, but for other reasons. If we have a look at solid and fission over and behind submerged reefs, I have a chapter in my thesis on that, then the KdV-NLFT can be applied for the identification of free and hidden solitons in incident and transmitted wave data. So sometimes we have free solitons, like in that signal that I has used as example with one leading solitons and trailing oscillatory waves. So I can explain soliton fission as a dispersion effect in shallow water, and it's simply because I have a stable wave that is traveling over a long distance in shallow and constant water depth. This wave shape has adapted to the boundary conditions, and it's a stable wave, it's a knoidal wave, it's a solution of the KdV equation, and suddenly this wave steps onto a shelf or on a water reef, and now we have wave shape that is that has entered different water depth, and now this formerly stable wave shape now is not a stable wave, because for this new water depth it is not a solution to the KdV equation, and therefore suddenly from here to here the formerly stable solitary wave becomes a transient wave. Suddenly it's composed from different stable shallow water knoidal waves and their interactions, and starting from here wave dispersion effects occur, because the different elements, the different knoidal waves have different celerities, and then you have wave dispersion. And if we apply if we know the initial wave shape, we know the new wave conditions, then we can predict the expected number of transmitted solitons. It's the same as here. When I have this wave, and I say I know the water depth, I can say what is the number of basic components. And I can do the same with a solitary wave shape from here. I just change the water depth, and I can predict what is the behavior of this wave if the water depth is constant. Something that is new, that is not addressed in detail, is the analysis of long-period primary ship waves. Primary ship waves are long-period waves due to the relatively small water depth in estuaries, and that's where we want to analyze them. KdV-NLFT decomposed ship waves into up to 70 solitons. It's a very long wave, and when I have this long wave of 16 seconds, I have 11 solitons. These waves are way longer, and so it's not. It sounds reasonable that we get such a large number of solitons, but we have to do a lot more analysis on that. We hope that this will provide new insight into the physics of ship waves, and that's definitely a future application of the KdV-NLFT. So, conclusion, the application of the KdV-NLFT provides explanations and solutions for different shallow water wave problems, which can be explained by the same physical process, by transient wave dispersion. And the conventional approaches, FFT, wavelet transform, and Hilbert-Rank transform, cannot provide these solutions. So now we come to the summary. And we have a successful numerical implementation of a nonlinear analysis method that considered the real physical wave propagation and interaction processes in shallow water. We have transient waves obtained from KdV-NLFT can explain different nonlinear physical processes such as long wave transformation, harmonic generation, and solid fission. For me, that's the most important point, because A lot of physical phenomena can be explained now, and the outlook is that we have a completely new point of view for the understanding of nonlinear shallow wave problems. That's what I mentioned. Transient wave, it's the keyword for that. And for the future, we can implement hyperfast modeling of 3D wave propagation in shallow water using theta functions. So once we know the underlying nodal waves at one position, we just can evolve the waves to another position, calculate the free surface. We do not have to do Ransworth simulations, but we can just use analytical wave functions. And that is, that's a big advantage for future processing and future wave generation and simulation. So thank you very much for your attention. So do you have any further questions? Do you want to know how the nonlinear spectrum of your data looks like? Maybe you're interested in a cooperation. Please see my website. The link is given here, or contact me. This is my email address. Well, I have finished my PhD 1 year ago, and now I'm going ahead to apply this method. I'm looking for examples, for partners, for ideas. So I'm open to everything, and if you're interested, don't hesitate, just contact me. Thank you for your attention and your patience for this long video.